Since their invention in the early 1900s, computers have completely revolutionized how humans understand and interact with the world around them. However, as the world relies on computers to process increasingly larger amounts of data, we begin to hit the physical and theoretical limits of classical computing. But what if there was a new kind of computer? One that could easily solve problems even our most powerful supercomputers struggle with. This is where quantum computing comes in, an emergent form of computation that uses quantum mechanics in order to surpass current limitations in computing. Quantum computing relies on the principles of quantum mechanics, importantly, superposition and entanglement. Quantum objects can exist in more than one state at a time. This means that a quantum particle can exist in multiple positions at once, for example. This is the principle of superposition. Superposition allows a quantum computer to act as if it has many more states than just the classical 0 and 1. This would allow a single quantum bit, called a qubit, to compute an infinite number of problems on its own all at once. The only thing stopping this from happening is the fact that only one state can be measured at a time. According to an article from MIT Sloan School of Business, despite this limitation, quantum computers can still tackle problems that are nearly impossible for today's machines. In addition to superposition, quantum mechanics allows two particles to exist in states that are completely dependent on each other. This property, called entanglement, is utilized in quantum gates, which change the superpositions of quantum particles. It is an essential part of the algorithms that give quantum computers their advantage. Some examples of these algorithms are Grover's algorithm, which can quickly search through databases, and Shor's algorithm, which can be used to break classical encryption. These algorithms have the potential to accelerate discovery in many scientific fields, and they can revolutionize encryption and cryptography. With advantages so immense, why aren't we all using quantum computers already? Quantum computers are fundamentally limited. First, being based on quantum particles, qubits are prone to decoherence, which is when a qubit gets interacted with by other particles and it forgets its superposition. This means many more qubits are needed than are theoretically expected, which makes quantum computers very expensive and limited in the number of calculations that can be made before errors build up. Also, quantum computers require extreme conditions to function, like near-zero temperatures, which make them impractical for daily use. So after looking at what quantum computing is, along with its major advantages and limitations, we can see that while the technology is powerful, it is not yet fully practical. The qubit's properties of superposition and entanglement demonstrate the field's potential to solve problems beyond classical computers' reach. But potential can only take us so far. The quantum devices today still struggle with issues like decoherence and high error rates, making them impractical for most real-world applications demanding reliability and long run times. So overall, quantum computers aren't ready to replace classical computing, but they have a real chance to become a powerful partner to it. As John Preskill, a Caltech professor and founding director of the Institute for Quantum Information and Matter, puts it, quantum technology is rife with exhilarating opportunities, and surely many rousing surprises lie ahead. But the challenges we face are still formidable. All quantumists should appreciate that our field can fulfill its potential only through sustained, inspired effort over decades. If we pay that price, the ultimate rewards will more than vindicate our efforts.